So we're now going to have statistical intervals for single samples for this PowerPoint presentation. This addresses to apply the course outcome applying statistical method in analysis of data. So we're going to construct confidence interval on mean of a normal distribution using either the normal distribution or the t-distribution methods. Constructing confidence interval on the variance and standard deviation of a normal distribution, construct confidence interval on a population proportion, and use a general method for constructing an approximate confidence interval on a parameter. Estimating mu. So the first parameter that we will be estimating would be the mean. If we are estimating means, um, there are two possible scenarios. We can have the large sample or the small sample. So if it is a large sample case, we're going to use the normal distribution. So for confidence interval on mean for variance known or large sample, if x bar is the sample mean of a random sample of size n from a normal population with unknown variance, so take note, the consideration here is that the variance is known. If variance or sigma squared is given, 1 minus alpha times 100% confidence interval on mu is given by x bar minus z alpha over 2 sigma over square root of n up to x bar plus z alpha over 2 sigma over square root of n, where z alpha over 2 is the upper alpha over 2 times 100% point of the standard normal distribution. For the sample size for the specified error on mean of variance known, if x bar is used to estimate uh, an estimate for mu, we can be 100 times 1 minus alpha percent confident that the error x bar minus mu will not exceed the specified amount e when the sample size would be n equal to z alpha over 2 sigma over e quantity squared. So this is the error. So it could be plus or minus certain amount of error. So for one-sided confidence bound on mean for variance known, a 100 times 1 minus alpha percent upper confidence bound, it would be mu equal to um, x bar plus z alpha of alpha sigma over square root of n. So take note that alpha is not divided by 2. It takes the entire confidence. For the lower confidence bound, it would be um, x bar minus z alpha sigma over square root of n equal to the lower limit, which is less than or equal to mu. For a large, if we will be having a sample size which is more than or equal to 30 for majority of other books and more than or equal to 40 for Montgomery, we will be using z is equal to x bar minus mu over s divided by square root of n. So s is approximately equal to n when n is relatively large. So we consider when n is greater than or equal to 30. So sigma becomes s. So it is a large sample confidence interval for mu with confidence level approximately 1 minus alpha times 100%. So for our examples, for a normal population with known variance, answer the following questions. What is the confidence level for x bar minus 2.14 sigma over square root of n up to x bar plus 2.14 over square root of n? So this is basically 2.14. So that would be equal to phi of 2.14 minus phi of negative 2.14. So we just evaluate this area bounded by this given interval. So 2.14 negative 2.14, so that would be 0.967643. For the second one, it would be phi of 2.49 minus phi of negative 2.49. It would be 0.98722228, while for 1.85 it would be phi of 1.85 minus phi of negative 1.85. So this is 0.935683. While for this one, this is less than or equal. So this is to the right. So 1 minus phi of, so this is less than. So the confidence level would be 1 minus, because it is on the right side, phi of 2. So, sorry, it should be only phi of 2. 0.97725. So this is 96.76% confidence interval. For the second one, 98.72% confidence interval. So for the next one, 93.57% confidence interval. And for the last one, the one-sided 97.73% confidence interval. Next one. For a normal population with a known variance, what value of z alpha over 2 would give 98% confidence interval, 80% confidence interval, and 75% confidence interval? So for this one, 1 minus alpha is 0.98. So alpha is 0.02. So alpha over 2 is 0.01. So we need to check for the value of z. That would give us 0.01. For the next one, we have 1 minus alpha is 0.8. So alpha is 0.2. So alpha over 2 is 0.1. So we check for z. While for the last one, 1 minus alpha is 0.75. So alpha is 0.25. And alpha over 2 is 0.125. We check the values of z that would give us the corresponding probabilities. So we should be checking our statistical tables for this to check what value would be close to these probabilities. So it is symmetric, so plus or minus would do. So we usually take the absolute value of z. And take note that if it is on the right side, it's positive, and if it is on the left side, negative. So for the first one, 0.01, 0.01 is, so for the absolute value of z for 0.01, it is negative 2.33. So we use 2.33. So it's negative, pero since we're considering we are just considering the absolute value for this one. So 2.33. For point 1, point 1 is negative 1.28. So we use positive 1.28. And for 0.125, the closest is negative 1.15. So we use 1.15. Next. Let's have avoided problem application. Consider the one-sided confidence interval expression for the mean of the normal population. What value of z would result to 90% confidence? What value of z would result to 95% confidence? And what value of z would result to 99% confidence? So consider the one-sided. So one-sided, so meaning we don't divide it by 2. So 1 minus alpha is 0.9. 1 minus alpha is 0.95. 1 minus alpha is 0.99. So here alpha is 0.1. I think earlier we have z is, for point 1 is 1.28. We would verify this later. So alpha is 0.05. So here z is 1.645. It is exactly between 1.64 and 1.65. And then for this one, alpha is 0.01. So z is, I think it is 2.33. So we don't divide the value by 2 if we're referring to two-sided confidence to one-sided confidence interval. The right side is positive, the left side would be negative. The life in hours of a 75-watt bulb is known to be normally distributed with sigma 25, and a random sample of 20 bulbs has a mean life of x bar equal to 1014 hours. Construct a 95% two-sided confidence interval on the mean life. Construct a 95% lower confidence bound on the mean life. Compare the lower bound of this confidence interval with the one in part A. Suppose that in exercise 8.14, 8-14, we wanted the total width to be two-sided confidence interval on the mean to be 6 hours at 95% confidence. What sample size should be used? For this one, you would be using the Excel sheet under confidence interval. So please check your Blackboard account regarding this one. I would be uploading the Excel sheet for you to work on the confidence interval. So for the first letter, for A, we have to consider that um, the mean is unknown, x bar is 1014, sigma is 25. For letter A, 1 minus alpha is 95% or 0.95. So two-sided confidence interval, and then n is 20. So when we are using this Excel sheet, take note that we are to fill up the green sides. So n is 20, sample mean is x bar 1014, and population standard deviation is 25. The confidence level is 95%, so 1 minus alpha is 0.05, and then alpha over 2 would be 0.025. So this is for two-sided, this is for one-sided. For its corresponding z-score, 0.05 would give us 1.90. For two-sided, so alpha over 2 is 0.025, we use 1.96 for z. For one-sided, 0.05, so we use 1.645. So substituting this on the formula for mu, which is equal to x bar plus for the upper minus for the lower, z sigma over square root of n, we can see these two values as the lower limit and the upper limit respectively. And then for letter B, construct a 95% confidence, lower confidence bound. So this is the lower confidence bound. So it is greater than or equal to 5.59. This is the lower confidence. So the lower boundary. So it is greater than or equal to 5.59. We just use the same formula, but for the lower limit, we use minus. For 8-17, if we wanted a total width, so the width is 6. So if this is the true mean, so this is x bar. So when we are approximating the total width, so that's 6. So we use the error to be 2, as that would be 6 over 2, which is 3. And then the population standard deviation is um, the population standard deviation would be 25, and so this should be 3. And then the confidence level is 95%. So we use 1.96. I think this is wrong. So from the formula, n is equal to z sigma over e quantity squared. So it would be 3 times 25 over 1.96 squared is 1464.23. So again, 3, that would be z, which is 1.96 times 25 over 3 squared. Sorry, this is 1.96 times 25 over 3 quantity squared. So n too thick. N is 266.77. So we use N is 267 um, light bulbs. Another example for estimation of the mean. An electrical firm manufactures light bulbs that have a length of life that is approximately normally distributed with a standard deviation of 40 hours. Find the 90% confidence interval for the population mean of all bulbs produced by this firm if a, if a sample of 30 bulbs has an average life of 780 hours. If a sample of 50 bulbs has an average life of 780 hours, and if a sample of 100 bulbs has an average life of 780 hours. So this problem makes use of standard deviation being 40 and then 90% confidence interval. So sigma is 40 and 1 minus alpha is 0.9. So that makes alpha is equal to 0.1 and alpha over 2 is 0.05. So z is 1.645 for this one. So we have mu is equal to, all of the x's are the same. So it would be 780. This is your x bar, plus or minus 1.645 times 40 over square root of n. If we will be using our Excel sheet confidence interval for one sample and considering for the mean, take note that on the first letter A, n is 30 with 90% confidence interval, so that would be alpha is 0.1 and alpha over 2 is 0.05. That would give us a z value of 1.645. The standard error is 40 over square root of 30, so that would be 7.3. So if we are going to multiply 1.645 to that, that would be the error, which is 12.01. So the confidence interval would be 767.99 up to 792.01. If we will be using n is 50, so this would change. N is 50. The standard error would be 40 over square root of 50, and the error would be 9.305. So observe that from 30, 768 to 792, when it becomes 770, it becomes 770 to 789. And when we have 100, the value becomes 773 to 786.6. So as you increase the number of samples, 30, 50, and then 100, the error or the confidence interval narrows. It becomes, the range becomes smaller. So this width of the confidence interval is your error, so the error decreases. So that is why it is advised that you choose a larger number of samples when doing your confidence interval or your testing of hypothesis or your inferential statistics. So if possible, increase the number of samples. Another one. The heights of random sample of 50 college students showed a mean of 174.5 centimeters and a standard deviation of 6.9. Construct a 98%, 95%, 90% confidence interval for the mean height of all college students. So we have n is 50. The mean of this sample is 174.5 and the standard deviation is 6.9. So mu is 174.5 plus or minus z of sigma over square root of n, which is 50. For this one, alpha is 0.02. So alpha over 2 is 0.01. So z is 2.33. For the second one, 2.33. For the second one, alpha is 0.05. So z is 1.96. So first one, 2.33. Second one, 1.96. For 90%, so z is 1.645. Plugging in your values, so when n is 50, when the confidence interval is 98%, confidence level, we have 172.23 to 176.77. Decreasing that to 95%, you have 172.58 to 176.41. And if you want to be 90% confident, you have 172.89 to 176.105. So what's the interpretation for this one? If you need to be more confident of your mean, um, if you want to be more confident on the location of your actual mean, it should be a wider scope. So you are 98% confident that the true mean would be falling between 172 and 177. You would be less confident if you narrowed the interval, and lowering the confidence level to 90%, the confidence interval also widens. These are the references used to create this lecture.